In 1897, a book was published in which a scientist discovered a chemical process to turn himself invisible. Since then, many movies and novels have glorified the benefits of being invisible. But is it even possible in the real world? Can we make matter invisible? A series of new quantum experiments have demonstrated that it is possible. Matter can be made invisible if we cool and squeeze it down to specific temperatures and densities. But what is the science behind it? Let me explain to you the basic principle behind it. But before that, we need to look at a couple of concepts that will be needed to understand the experiment. Particles in the universe can be classified into two major categories based on their quantum mechanical spin: fermions and bosons. Fermions are particles with half-integer spin, such as -3/2, -1/2, +1/2, and so on. On the other hand, the bosons have integer multiple spins 1, 2, and so on. Fermions include quarks and leptons. Quarks are the elementary particles that make up composite particles such as protons and neutrons. A famous example of an elementary lepton is the electron. Talking about electrons, in 1925, Wolfgang Pauli came up with an interesting principle known as Pauli's exclusion principle. He stated that no two electrons having an identical set of all the quantum numbers can occupy the same state within a quantum system simultaneously. It's like saying that if we consider two identical twins as fermions, they can never stay in a room together. It has to only be one at a time. Although it is formulated for only the electrons in the first place, it was later extended to all the fermions. It is this principle that keeps atoms stable, because without it, all of them would collapse together while releasing an enormous amount of energy. Pauli's exclusion principle is the backbone of turning matter invisible. This is because only a finite number of energy states are present at the quantum level, where electrons can stack themselves up. Several unoccupied energy levels are available, so when an atom is bombarded with photons, the electrons absorb energy and jump to higher levels. Then, when they again come back to a stable lower energy state, they emit the extra energy, and in this way, the incoming light is scattered, and we see an object. But things become different at lower temperatures. The temperature of an atom is directly related to its energy, so when a cloud of atoms is cooled down, they lose energy. As a result, they fill all of the lowest available states and form a type of matter called the Fermi sea. These particles are so tightly packed that they cannot move up to higher energy levels or even drop down to lower ones. In other words, the electrons have nowhere to go. When light strikes an atom in such a state, the photons cannot interact with the atoms, or more clearly, the electrons present inside. So, the incoming light simply passes straight through them without being scattered. And in this way, the atoms behave as if they weren't even present in the path of light, eventually becoming invisible. This phenomenon is known as Pauli Blocking and was proposed around 3 decades ago. However, it is the first time the principle has been practically demonstrated in a lab. It took decades to achieve this experimentally, because getting an atomic cloud to this state of causing invisibility is very difficult. It not only needs incredibly low temperatures, but also requires the atoms to be squeezed to record-breaking densities. To achieve so, researchers captured lithium gas inside an atomic trap. Later, the atomic cloud was bombarded with lasers. The laser beam was tuned so that it collided only with those atoms moving in the direction opposite them. Eventually, the atoms lost their momentum and slowed down. As a result, and indirectly, they also cooled down. This technique of cooling atoms is known as laser cooling and is widely used in making studies at frigid temperatures. Researchers could freeze their lithium cloud to 20 microkelvins, which is just above absolute zero. Then they used a second and tightly focused laser to further squeeze the atoms to a density of roughly 1 quadrillion atoms per cubic centimeter. After carefully cooling and compressing the atoms, there came the final task. The team shone a third and final laser beam toward the gaseous cloud to check whether they were successful. The beam was carefully calibrated not to alter the gas's temperature or density. Further, researchers used a hypersensitive camera to count the number of scattered photons from the final beam. And what they observed was simply amazing. As predicted by theory, the cooled and squeezed atoms scattered 38% less light than those at room temperature. This made them significantly dimmer, which means that if we can squeeze atoms more precisely at lower temperatures, we can make matter invisible. Not only this, but 2 other independent teams also cooled down 2 other gases, potassium and strontium, to show this effect of Pauli blocking. Although the enhanced applications of this effect seem to be theoretical at present, such small steps can play a significant role in controlling the working of the atomic world. Also, these experiments have strengthened our hopes of achieving invisibility in the future, although at quantum scales to begin with. If you're interested in studying astrophysics at home, make sure to check out our Basics of Astrophysics series, the link to which is given in the description. This series explains everything at the most fundamental level, from the EM spectrum to telescopes, and from the birth of stars to the formation of black holes and galaxies.